And welcome to High School Physics Explained, and today I want to specifically talk about Coulomb's law. But before we start, let's quickly remind ourselves about the nature of electric fields. If you remember in a previous video, I discussed the fact that if an object has a certain property and is placed in a certain field, it will experience a force due to that property. So we have gravitational fields, and you need mass to experience a force in a gravitational field. You have magnetic field, where a magnet or even a ferric metal experiences a force in a magnetic field. And of course, electrons or objects with charge experience forces in electric fields. So here I have a little charge. We know it has a charge because it experiences a force in an electric field, and this really red spot here represents an object that is creating that electric field. In this case, my object here is a positively charged object, and as a result it has field lines going away, and that is of course the force experienced on positive charges. So if this is a negative charged particle, it will be attracted towards that. So that will be the force, and the electric field is defined that way. It's the force per unit charge. But the truth is that the force exerted on this charge here by this charge is equal to the force that this charge experiences due to this charge, that there is this mutual force between them, and it's not just dependent on this charge, it's also dependent on this charge. So let's explore that. So here I have a positive charge. I'm going to put another positive charge that is roughly the same size. What is going to happen when these two are in vicinity to each other? Well, because they are the same charges, you know that they will repel. If I were to hold it there, that force, of course, I have to apply to hold it there. What would happen if I bring them closer? What would happen to the force? Now, you would know that probably that the forces increase. And so if I take this further away, the forces decrease, like so. Again, they would repel. Similarly speaking, if I have a negatively charged object, in this case, I have a force between them that is attractive. If I move it closer, the forces are stronger. If I move it further away, the forces are weaker. So there's this sort of inverse relationship going on here. But if I increase one of the charges, not in mass, but in the size of the charge, like so, then the forces between them will increase. And so whether I increase this charge or whether I increase this charge, that will also affect how much force it is exerted on each other. Let's explore this. So here I have two charges, and you can see that these two charges here are labeled as Q1 and Q2. Now, for all intents and purposes, I'm going to be using the same shape here, but I want you to appreciate the fact that the charges could actually be different values. And in this case, they exert forces that are attractive. And I want to particularly highlight the fact that the forces here are mutual. That is, the force due to Q1 on Q2 is equal to the force of Q2 onto Q1. That's an application of Newton's third law. So if I change any of the parameters here, change any of the variables here, then the forces that each other exert on the other will be exactly the same. Now, in this case, we've got attractive, and it could be repulsive if they are the same charge. But what does it depend on? Well, the first thing you need to understand is that the force that I have is certainly going to be dependent on each of the individual charges. So both Q1 and Q2 will determine the strength of the force. But it's not only that, it's also the distance between them. But you know that as the distance increases, the force decreases. If you were to mathematically determine the values of the force as the distance increases by a set factor, you will notice that as the distance between them increases by a certain factor, the force actually decreases by a square of the distance. In other words, what we're saying is that this is an inverse square law. And I do have a video where I discuss the inverse square law more closely. And so what we say here is that the force is proportional to the product of the charges, but inversely proportional to the distance between them squared. If I were to double one charge, the force doubles. If I double the other charge, the force doubles. If I double both charges, the force goes up by a factor of 4. And of course, if I double the distance, times 2, then the force decreases not by 2 but by 4, a square of the factor. Now, I'm almost there to the formula for Coulomb's law. What if I took this section here like so, and then what I do, if I got F and divided it by that value like so. So in other words, what is F divided by this value? If it's a proportionality, then this ends up being a constant value. Right? So if anything is proportional in that sort of relationship, then if you do one side, the dependent variable, divided by the independent variable, which is on the other side of the proportionality symbol, then this would graph into a straight line. So this is F and this is Q1, Q2 over D squared. I would get a straight line. And of course, the slope is a constant. So if I now have this relationship here where F is proportional to this section here, and I want to replace the proportionality here with an equal sign like so, I need to here have a constant value, which would be the slope of the line that I just showed you before. And what is that constant? That constant is a value of 1 over 4 pi E naught. Now, some of you are saying, what is E naught? Well, E naught is called the permittivity of free space. Now, the actual value is this, and it's one of the constants in the universe. This is a value that is the same everywhere. And so 1 divided by 4, multiplied by pi, and the E naught value, times all this gives you the magnitude of the force. Now, fortunately for you, is that this particular value right there approximates to 9 by 10 to the power of 9. So we often refer this as the electrostatic C constant. So we can call it C. So in other words, we get F is equal to C Q1 Q2 over D squared. But this is actually more precise because it links to one of the universal constants. But you can use this value here as a pretty good approximation for any calculations that you need to do. And so let's do that as an example. Well, let's do a calculation that shows us the force between two specific charges. So here I have a question where I have a hydrogen atom that has a very simple structure. Of course, most of you are aware that the hydrogen is simply an individual proton, and surrounding that proton we have an electron that is in orbit, and I've drawn this really accurately. Of course, this is a simplified planetary model. The reality is a little bit more complex, but for our question, it'll serve its purpose. And the question is what is the force of attraction between my little electron that is going in orbit around my nucleus of a single proton? Well, of course, what you do is you write down the variables that you know. And so the charge on my proton is positive 1.6 by 10 to the power of negative 19 Coulomb. We know the charge on my electron is exactly the same value. That is also equal to 1.6 by 10 to the power of negative 19, but of course it's a negative charge. And the distance between we have is 5.3 by 10 to the power of negative 11 meters. Notice we are in SI units. And the question now is, what is the force? Well, here we go. Force is equal to C Q1 Q2 over D squared. So we substituted in the value from 9 times 10 to the power of 9, and we multiply that. Now these two values are exactly the same number. Of course, the plus and minus aren't about direction, they're just simply about the actual type of charge. So we might as well just say 1.6 by 10 to the power of negative 19, and we'll square it because we've got two of them. And then over here we have the distance between them, which is 5.3 by 10 to the power of negative 11. And of course we have to square that. And when you calculate all that out, you get a value of 8.2 by 10 to the power of negative 8 newtons. Now that's a very small force. But remember, we are dealing with extremely small particles here. So actually this force is quite significant in terms of the effect on my proton and on my electron. You can see the order of magnitude here is negative 31 in terms of mass and negative 27 of mass, and we've got an order of magnitude of roughly negative 7 over here. What if I wanted to know, well, what's the gravitational force between these things? Now, again, you probably need to know the gravitational formula here, and if you don't know, I'm going to give it to you, but it's actually a similar formula. The gravitational force between two objects is equal to the value of G m1 m2 over d squared. Notice the format is very similar to Coulomb's law. So we have a constant, and that constant, by the way, is equal to 6.67 by 10 to the power of negative 11. And of course, now we have the masses and the distance. So if we substitute that in, we get 6.67 by 10 to the power of negative 11. There's my G constant. My two masses now, of course, are different. 1.7 by 10 to the power of negative 27 for my proton, and 9.1 by 10 to the power of negative 31 for my electron. We divide this, of course, by the distance between them, and that is 5.3 by 10 to the power of negative 11. And of course, we have to square that. And so when we calculate that out, we get a value of 3.7 by 10 to the power of negative 47 newtons. Now look at the variation between the force due to electrostatic attraction and the force due to gravitation. It shows you that one of the fundamental forces, that is gravity, is significantly weaker than the electrostatic force, which is another one of the fundamental forces in nature. There's a huge difference, and in fact, if you calculate the variation, the variation is about 2.2 by 10 to the power of 39 as a factor. That's huge. But that I slightly digress here. I hope you understand Coulomb's law here. I hope that has helped you understand Coulomb's law. I'm Paul from High School Physics Explained. Please like, share, and subscribe to the channel for further updates. And don't forget to hit the little bell to get notifications. Bye for now.